break from the study, and now you're ready to get back to the last 3 weeks in this semester, and also the final exam, hopefully. Speaking of the final exam, I believe you have received the email from Irene about the arrangement. So there are 2 time sessions, and in each session we have 3 rooms in these computer labs. And you'll be assigned to one of these sessions and one of the rooms. And you can choose any computer, any seat in the room you're assigned to. We will create a special exam account on the computer for the exam. So you don't need to log in with your account. And of course, you're cut off from the internet. And you can only access the software that we'll be using for the exam. Okay? And this is an open book exam. You can bring in hard copies, but no soft copies. But due to the limit of the time, I strongly suggest you to study all the materials carefully beforehand, so you don't print out and bring everything here, because you won't have time to search through them during the exam. Any questions about the exam? Yep.
How do you get people normally prepare for the exams? So, like, normally I know that we learn a few practice exams or something like that. How would you do this?
Right, so the questions in the final exam will be very similar to the ones in the projects, from the first one to the third one. So you can expect very similar questions in terms of what data you're given and what answers we're expecting. A bit more information about the exam. You have, I think, 5 questions. The first 2 are hand sketching. Third one is AutoCAD drawing. And the last 2 are the GIS problems. So they will be similar to questions in project 3. Sorry? No theory? No, there won't be any theory questions. But again, it's very important for you to understand the theories from these lectures, so you know what tool you want to use when you're given a certain type of data, when you're asked to produce certain results. You know what analysis tools you want to use, especially in the GIS. All right, in addition to the exam, another housekeeping thing. So the statutory evaluation is open now. So I hope you can take a few minutes and complete the survey. This is very important for this class. We really want to hear your feedback, what we did right and what we can improve in the future. We do look at the statutory evaluation, your feedback at the end of the semester, and try to address them in the future offering. So since we're in the computer lab, so maybe at the end of this class, take like 10 minutes to complete it, or later. I don't know what's the window for the evaluation, but make sure or try your best to provide your feedback. All right, so let's get on to this week's content. So this week we'll continue the topic of spatial data analysis in GIS. This is the second part, and in the first part, well, it's already 2 weeks ago. Let's try to remember what we have learned. So we talked about the spatial query. How do we select the features with certain attributes or certain geometry from the vector data? So that's query by location and query by attributes. And then we talked about the geometric measurement, where we calculated the the distance surface and then cost surface. And at the end, we were computing the least cost path given the cost surface. So today we're going to continue the spatial data analysis topic, we're going to talk about two very important techniques or set of techniques, which is overlay analysis, map algebra, and spatial interpolations. The overlay analysis. So here we're trying to put together different data layers which are registered to a common georeferencing system in order to analyze the relationships between the features or the values at each location. So here we're putting together different data sources and different data models and try to get more insightful information. For example, here in this example, we're trying to figure out what's the proper location or what's the level of vulnerability to nutrient runoff in this area. So we want to overlay different data, including the slope, where the streams are. And again, we can use the geometry tool to create a buffer around stream. You have all done this in the exercises. And then the land use and soil types. So how do we stack all this data together to get the insightful information from them? So this is what overlay analysis does. And different from the query by attribute or query by location that we learned last week, overlay analysis can be used for both vector and raster data. However, the way we deal with vector and raster data are different in overlay analysis. And we'll start with vector overlay. So in vector overlay, we're trying to combine geometries as well as their attributes from different input layers into a single output vector layer. If you look at this example here, we have two input data layers. So they are in polygon feature class, and they're representing different information. So different level of rainfall and different types of soil. And now we want to figure out what's the best growing area for the grape. And now if we do overlay analysis of the rainfall and soil type data, we can create a new vector data, which represents the different areas with different soil type and rainfall level. So now you can see in the output, we have 6 polygons now as a result of the geometry from the 2 input layer. And for each of these 6 polygons, we also have new attributes. So the rainfall level and soil type from different input layers. So this is in general how we overlay vector data. And depending on what's the feature class of this vector data, so we're talking about points, lines, and polygons. Depending on the types, we have different overlay types. So the first one is point in polygon overlay. So this is not really a method or tool in ArcGIS, but this is different examples of how we overlay different feature classes. So in polygon overlay, we're trying to identify which area a point feature is located. So we have an input layer in point, and we have another input layer in polygons. So now if we do the overlay analysis, the results are still the point features, but we combine the attribute from the polygon features to the point. So now as a result, you know those observations of the birds. Where did they happen, right? So they are observing different vegetation types. And here is a more visual illustration. So you have a layer of points, and then you have a layer, again, with the same georeferencing system. So they're representing the same area. And now eventually you have output vector, and then with the attribute that contains the information from the polygon layer. So this is point in polygon overlay. And the next one, as you can imagine, is the line in polygon overlay. So now, different from the points, the line can cross different polygons, right? So when we do the overlay with the input of line feature and the input of a polygon feature, we can get an output vector in lines, but now the lines are broken up based on the boundary of the polygons. So now we have the road vector here, but because we overlay the soil types vector features, so we know each section of this road was the soil type for that section of the road. So this is line in polygon overlay. So we get information from the polygon layer and then include that into the line feature layer. And in this case, we'll create new IDs because we have new sections for the road. So instead of just 3 sections, we now have 6 sections because of the different soil types. Okay. And lastly, we have polygon on polygon overlay. So in this case, both or all of the input vector layers are in polygon. And we can do a union of all the boundaries of these polygons and create new polygon areas in output feature. And because each of these polygon contains its attribute, in this example, the first one represents the land use, the second one shows the soil types. So now with the new polygon created, you can see they're assigned with different ID numbers. And for each polygon, you have the land use attribute and soil type attribute. So this is polygon on polygon overlay. And this is based on the types of the input features. And vector overlay can also be classified based on different ways they are overlaid. So in these 3 cases, they are basically treated equally. But in vector overlay, we can specify the priority or what information we want to keep, what attribute we want to preserve from the overlay operation. And also, in many cases, the data layer may not overlap perfectly. So they may have different geometry, different extent. So what will happen if we overlay them together? So there are 6 types of overlay operations. So all of them are trying to join 2 existing set of features together into a single set. And these 6 types are defined by different spatial relationships between these input features. So later, if we open the ARC toolbox, we'll be using some of the tools in ArcGIS. So under the overlay tab, you will find there are 7 different operations. So spatial drawing is a little bit different. We're not going to talk about this. So we're going to talk about the erase identity, intersect, symmetrical difference, union, and update. So from name, you can tell they are overlaid in different ways. So the first one I want to talk about is erase. So this is probably the simplest one. So in erase, we're trying to create a feature class by overlaying the input features with the erase feature. So in this case, you have to specify which one is the input, which one is the erase feature. Because in this operation, the input, in this operation, only the portions of the input feature falling outside the erase feature are copied to the output feature class or the output vector data. So this illustration shows you how it works. And this is the erase window or erase tool in ArcGIS software. So you need to specify what's the input feature and what's the erase feature. And when you use it, make sure in the output feature class, you name the file properly so you know what this output is representing. And let's think about when you may want to use the erase operation when you deal with vector data. So in what scenario you may want to subtract a geometry or polygon from the other polygon. But let's say we want to build a campsite around a lake, and the campsite has to be built within 200 meters from the lake, so people have access, easy access to the lake. We can do a buffer operation to find the 200 perimeter, right? But what if as the output we just want the areas we can build a site? So want to exclude the lake. So in this case, you may want to use the buffer we created as the input, and then the lake geometry as the erase feature. So after the operation, you will get basically the ribbon around the lake with 200 meter buffer, but without a lake. So this is one example when you may want to use the erase operation. And the second one is intersect. In this case, we're trying to compute a geometric intersection of the input features. And here we can have more than 2 input features. And the program will find the features or portions of the features which overlap in all the input layers. And they will be written into the output feature class. So in this case, basically we're doing a and B operation. So identify only the overlapping area. So let's say if we will have 2 input features. And here you don't really need to specify which one is the input, which one is the intersect feature, because it will only identify the overlapping area. And in this window, in this tool in ArcGIS, you can include more than 2 input features from the drop-down menu, as long as they're in your project folder. And then again, specify the output class. So in this case, we have to think about how the attributes are transferred or how the attributes are altered after this operation. So let's say in the input feature, we have 2 polygons, and they have the attribute of 1 and 2. And then for the circle feature as another feature input, we have the attribute as A. Then in the output, we identify the intersections. So the left part will have 1 and A. The second will have 2 and A. All right, so this is how the attribute is also combined in the overlay operation. And then the third one is union. So this is basically A or B. right? So we're trying to compute a geometric union of the input features. Again, you can have multiple input features. And all features and their attributes will be written to the output feature class. So let's say if we have same 1, 2, and 8. So now this part will basically have 1 and 0 or null. So 2 and 0. And this part will have 1A, 2A, and then 0A. Okay, so that's how the attributes are transferred in the union operation. And very similar to the intersect tool. Here you can specify different input features, and then the program will do the union operation for you. So this one is called symmetrical difference. So this is basically the exclusive OR operation. So A or B, but not A and B. So basically it will subtract the overlapping area from these two inputs. And you may think, okay, I can do this with the union and intersect operations, right? You can do a union first and subtract and do a intersect operation and then subtract these two. So you can get the same result. But here, ArcGIS provides you with the symmetrical difference tool. So you can do that easily with just one operation. And in many cases, this is very useful. Imagine if you want to identify the area that is impacted by one of the features. For example, you have the buffer zone with the influence from the road noise and the chemical pollution, for example. And you want to find an area you can build a house with the impact of only one of these factors, but not both. So you can use the symmetrical difference to find that area. So now the last two, identity and update. So identity is more concerned about the attributes. So here, in identity, we're trying to compute a geometric intersection of the input features and the identity features. So in this case, you need to specify which one is the input and identity, because the input feature will preserve its geometry, but the identity feature won't. So it will only contribute the geometry that intersect with the input feature, and also contribute the attribute to the overlap. So let's look at this example. So we have a identity feature as the yellow rectangle. And then if the features in the input cover is A and B, and the attribute in the identity feature is 1, then this is what you will get as the output. So you will get the geometry for the size of the input feature, but then the overlap these two sections from the identity feature. And also the attributes are included from the identity feature. Okay, so this is less commonly used, but you need to understand how this one works and what geometry or attribute will be preserved in the output layer. And update is very similar. So we have the input feature and the update feature. But in this case, we actually keep the geometry from the update feature. And the update feature geometry will overwrite the features in the input feature. So you see this circle here is the update feature. And in the output, it will overwrite the geometry in the input feature. So you won't see these boundaries here. And as a result, if you have this input feature here and update feature, so you can see they're of different size, right? But their center are the same location. So when we do the overlay, when we do an update overlay between these two, you will get this result. So you'll see these edges are overwritten by the new feature. So it creates a new polygons. And the attributes from these two input features are also preserved. So you create new polygons with new attributes. Okay. So the identity and update are only used in very specific situations. But the first four, or first three, erase, intersect, and union are very commonly used. So very likely you'll be using them in your project and exam. So pay very close attention to them. So that is vector overlay. And now let's talk about how we overlay raster data. So as I mentioned earlier, the way they're overlaid are very different because of the nature of these different data models. So in raster overlay, we combine multiple raster layers into a single raster, where every cell of each raster references the same geographical location. So first of all, we need to make sure they're referencing the same area, same location. And then the overlay involves the operations on individual values of corresponding cells. So if they are describing the same area, then each cell on these different rasters should be correspondent. And then after the overlay, raster overlay operation, we create a new raster layer. So we're not changing or modifying the existing layers, but creating a new raster as a result. So because the raster data model are represented in the grid of cells or pixels, so there's no involvement of geometric intersection or geometric operation. So basically in raster overlay, we only care about the values in each of the cells in the input rasters. Here on the right side is an example. So we have the land cover types in a raster format, and then the slope classes. So there are three classes for the slope: 0 to 15, 15 to 30, and above 30%. So the values in each of these two rasters represent different information. And when we overlay them together, we create a new raster. And with the new raster, we can say, okay, we can do a reclassification. So because each of these has only three classes, right? Three classes, and eventually we can get 8 classes because they have different combination of the cover type and slope percentage. So this is similar to what we have in overlay, in the vector overlay, where we get the attributes from different vector layers. But with raster, we can do actually much more with these values. So in addition to addition or subtraction, we can do other mathematical operations or other conditional operations. So the raster overlay, in raster overlay, we're trying to use mathematical operations to combine the rasters assigned with numerical cell values to calculate a new value for each cell in the output raster. So here is one simple example of the addition operation. So we have values in the two input rasters, and with addition operation, we just add the value in each cell together. And we can also do a conditional operation. So in this case, the operation is A and B or A or B. And the input feature may represent different information. For example, here, it has three classes. I don't know what they mean, but let's say there's F, L, and G. And then in another input, we have 3, 4, and 5. So in this case, we only care about what is the cells, what are the cells that has the F value from raster A, and also have the value of 4 in raster B. In this case, we can do a reclassification first to find what are the cells with the class F. And then this raster becomes a simple binary raster containing only 1 and 0. So 1 represents true and or yes, and 0 represents false or no. And same for the other one. So now we can easily do a conditional operation to find the cells that are both 1 in these two new rasters. So this is the underlying process of how the conditional operation is done in the raster overlay. But with the tool provided in GS, in ArcGIS, you can just do this with one click. You don't need to do the reclassification process. But this is how it's done behind the scene, okay? So this raster overlay is done by map algebra. So I mentioned this in the select by attribute or the calculation for the vector data. So this is how the computation is done with raster data. And this is a common tool in most of the GIS programs. In ArcGIS specifically, it uses a tool called raster calculator. So you'll be using this a lot in this week's exercise, and perhaps very likely in the exam and project as well. So I think I have another slide for that. Okay, as I mentioned, there are different operations. So the map algebra allows you to do arithmetic, logical, relational or comparison, conditional, trigonometric, and statistical functions. So with all these operations, basically you can do any analysis or computation with the values in the raster data. And we'll see many examples later. And this is the tool of raster calculator in ArcGIS. So when you add the data, add the raster data to your project, they will be shown here as the layers and variables. And this window here shows all the functions you can use. This is similar to what we did with the SQL in select or in the query by attribute, right? When you want to find the features with the attributes you're looking for. But in this case, you're not doing only a conditional selection, but also some mathematical computations. So here, if you double click on one of the layers, it will be added to the expression window. And then you can type in the operators to complete your equation. For example, if there's a relationship between the degree of the slope and the cost to build a wind turbine there, then it has to be represented by a function first. And then here you can get the slope degree input from the slope layer, and then implement the function here to get the cost result. So in that process, the output will be a cost raster. Okay? And when we do the map algebra, there are actually different types. So the map overlay, basically we care about individual cells, right? We want to combine or compute a new value based on the value from the same location from the input rasters. So this is called a cell-by-cell analysis. So we're looking at a single cell, the same cell in each of the input rasters. And then we implement a equation or function and compute a new value. And this new value is assigned to the same location on the output grid or output raster. And this is called a cell-by-cell analysis. And there are also other types of analysis, and we actually have been using them so far, but without realizing. But I'll give you some example. So the second type is called focal or neighborhood functions. So instead of looking at individual cells, now we're looking at an area or neighborhood. The result will still be one cell on the output raster, but to compute this value on the output raster, we're looking at a neighborhood or area on the input raster. So now the function for the output becomes a function with the input of the neighborhood shape and the input raster. So this illustration here shows you to compute this value on the output layer. We're looking at a bigger area on the input layer. And then how we compute this value on the cell could be any operation we specify. It could be a sum of the values. It could be a mean value of all these cells in this neighborhood, or it could be the maximum or minimum value, depending on your need. Okay? And just one application of this, if you have a elevation raster, a raster representing the elevation of a terrain, the data is very rough, so you want to smooth the surface. So this is the method you can use, right? So you're taking an average of an area and assign the average elevation to that cell. So eventually you will get a smoother terrain or smoother elevation output in your output raster. And for the size and shape of the neighborhood, you can define yourself depending on the application. And there are different types of neighborhood. It could be a rectangle, could be a wedge, indicating a specific direction, or a circle, or a annulus. And you can define the parameters of this shape to define what or to what extent the cells in the input layer you want to consider. And you can also define an arbitrary kernel, so arbitrary area that you want to consider. And this kernel is described by an additional raster. So in this raster, you basically specify the weight of of the kernel raster, the kernel areas, which cell you want to consider, and what kind of value you want to, what kind of weight you want to give to each cell. Or it could be just a binary raster. Basically, you tell the program which cells you want to consider. The cells with the value of 1. And very quickly, how this focal or neighborhood function works. So basically, if you have a rectangle neighborhood here, you want to do a moving window operation. So this is what the program does in the background. So if we want to find the mean value of this cell here, so basically I use a rectangle area here and find the mean value of all these cell values and assign the mean value to this point, to this cell. And after the computation of this cell, the window will move to the next cell. So for this cell here, or same here, the new window will be created and calculate the mean or other operations or other result you want to get, the range or majority of the value. So this is called a moving window computation. All right. Now the third type is called a zonal function. So in this function, we're taking in the data raster and then the zone layer. So in the zone layer, we specify different zones. It could be the soil type or different land use. And in the zonal function, we compute a new value for every cell in the output raster as a function of the values of the cells here, of the cells belonging to the same zones. So here we have the zone layer, and then we know which cell belongs to which zone, and then we overlay this zone information to the data layer. Now when we do the computation, whether it's calculating the mean or the maximum, we only care about the cells within this zone. And as a result, each zone will have the same value using the result of the computation. So here is one example for you to better understand this. So we have the forest raster. This is the zone layer. So 11, 12, 13 represents different types of forest. And we have the elevation layer, which is the data layer. So now we want to know different types of forest. What's the mean elevation or what's the maximum elevation? So now if we use the zone function here, you will see for all the zones with a type of 11, you'll find only the elevation values in these cells. And then in the output raster, you'll see cells, all the cells in these zones have the same value as a result of the mean of all these values here in the elevation raster. Okay, so here is how you get the mean elevation for different cells in the same zone. Okay, so now all the cells belong to that zone will get the same value. And it's the same for the maximum operation. So you see all the cells within the 11. Yes?
Sorry, so is this basically just the way of applying an average of values to something else?
An average of...
So like taking the average of one layer and adding it.
Well, not necessarily. It depends on what you want to get. So here, mean is just one operation. you can do maximum or a range or majority. So in this case, mean is just getting the average elevation, but you can find the maximum or minimum elevation for that zone. So the point or the unique thing about zonal function is you're not looking at individual cells. So you compute the value for the cells based on which zone they belong to. So if you look at the output raster, you see the value are defined based on the zones, right? So although they don't include the zone class anymore, but their value are calculated based on different zones they belong to. And finally, there's the global function. So here we calculate the value for every cell in the output raster as a function of the existing values of all cells in the input raster. So if you look at this illustration here, the comparison between the local, focal, and zonal and global functions, you'll see the difference between them. And in global, we are looking at all the cells, all the values in the input layer. So if you can still remember what we did last week, the distance surface and least cost path function. So that is actually a global function because in order to compute the least cost for each cell, we're actually looking at all the cells. We traverse all the cells from the start point or the destination to this cell. Okay, so that is one example of the global function. So basically, in order to compute the value in this cell, we're looking at all the cells. And differently in zonal, we're only looking at the cells that are within a certain zone. And in focal, we're only looking at the cells within that neighborhood that you define. And in local or cell by cell, we are only looking at the same cell, the cell in the same location. Okay, so that's the fundamental difference between these methods. All right, so that's the first part of this lecture, overlay analysis and map algebra. So here a very quick rundown of the tasks you will be doing in the next 30 minutes. So the first task is to identify the potential campground sites. So I've already gave you this example earlier when we talk about intersection and vector overlays. So here you're going to create an area that is within 200 meters from the lake and 300 meters from the road. So that's 2 buffer. And you'll be using the different vector overlay tools like intersect or erase to find the exact areas that you can build a campsite. Again, here you want to exclude the lakes, okay? And the second part of task 1 is the raster overlay or the map algebra. So here you're giving a function, which is a function of the distance from the road, okay? So here you want to compute the cost based on this function for you to get from each cell to the road. And with map algebra, you can also do a conditional selection. So here you're asked to find the cells or the areas that has a distance cost less than 150. So in order to do this, you can use the conditional operation in the raster calculator. And finally, you're given a cost function based on the slope angle, so from the DEM data. And similarly, you're computing a area based on threshold of 50, given the cost calculation. All right? Okay, so let me know if you have any questions. And the tutorial material instruction is on the Moodle site.